Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 12 on Bootstrapping. Today we're going to talk about the tool of bootstrapping, which is an incredibly useful, handy result in statistics that you can use in a variety of settings. It sort of coincided with the personal computer revolution, and so it gives us a way to avoid an awful lot of mathematics in biostatistics. Before we talk about the bootstrap, we're going to talk about the Jackknife, which is a precursor to the bootstrap. That is, as its name suggests, a handy little tool. So let's talk about the Jackknife here briefly before we go into the bootstrap. The Jackknife is exactly as its name suggests, a handy little tool. The bootstrap, on the other hand, is like an entire workshop of tools. The key idea in both the Jackknife and the bootstrap is to use the data, so-called resampling of the data, to get at quantities that are difficult to get at otherwise. For example, variances and biases and that sort of thing. Now, we don't need either the bootstrap or the Jackknife for something like the sample mean, where we know all of its theoretical properties. But for other less obvious statistics, we need something that does it for us. And, it'd be preferable if that something didn't require a year of mathematics just to get us to the starting point. In contrast, the bootstrap is you dream up a statistic or something like that, and you want to estimate a standard error with it, you can start bootstrapping it immediately. So let's talk a little bit about what the Jackknife does before we begin with the bootstrap, because sort of historically the Jackknife came first. The first use of the Jackknife was by the statistician, I'm going to butcher his name, but I think it's pronounced Quinui. And he used the Jackknife to estimate bias, I believe. Then the Jackknife was really popularized and further refined by the extremely well-known statistician John Tukey, who we talked about a little bit in the lecture on plotting. Tukey had numerous inventions, including the fast discrete Fourier transform. He coined the term bit for binary digit. He was the first person to do that. Anyway, he did lots of things, invented the box plot. I think when you see it, you'll conclude along with me, the Jackknife's a handy and an incredibly clever thing for someone to think of. So the idea behind the Jackknife, and similar to the idea behind the bootstrap, is you have something that you don't know, like the bias in a statistics or the standard error of a statistic, and the idea is to use the data to get a sense of it. Well, what the Jackknife does is it says, okay, well, one way to get at these quantities is to take one of the observations out and then formulate the statistic on the remainder and see how well the statistic does, at estimating that one pulled out observation. And this is very related to the idea that you frequently hear of in machine learning and statistical prediction of so-called cross-validation. The Jackknife tends to have a different goal, in that the goal of the Jackknife tends to be bias estimation or variance estimation. But the principle is very similar in that you're deleting observations. Leave one out cross-validation is typically used as an estimate of prediction error. So anyway, let's just focus on the Jackknife, and if you take classes in machine learning or something like that, you'll talk about cross-validation. The Jackknife deletes one observation and calculates whatever estimate you're thinking of based on the remaining n-1 of them. And then it uses this estimate based on n-1 of them, in which you get n estimates having left out one observation one at a time. It uses these n estimates to do something like estimate biases and standard error. And again, note, we don't need this for the sample mean. We know that the sample mean is unbiased under certain assumptions, and we know exactly what the standard error of the sample mean is under the standard setting. So the Jackknife isn't necessary for those settings, but it's maybe necessary for other ones. So let's just consider the Jackknife for univariate data, and let's let x1 to xn be a collection of univariate data points where we want to estimate a parameter theta. And so let's let theta be the estimate based on the full data set, and then let's let theta hat sub I be the estimate of theta that you obtain where you use the n-1 observations obtained by deleting observation I. And then let's let theta bar be the average of the leave one out estimates. So with that notation in mind, the Jackknife estimate of the bias of our statistic theta hat is just n-1 theta bar minus theta hat. So let's kind of consider the principle of this before we get to why in the world that n-1 is there. So theta hat is our estimate, looking at how close it is to the averages of estimates where we deleted an observation each time is exactly going to give us a sense of kind of population level bias. And then you might wonder, where in the world does this n-1 come from? It's a factor that's based on for example, the sample variance, where you would estimate the bias of the sample variance. It would give you the correct answer. The n-1 is sort of calibrated by statistics that we actually know. So again, this estimate is really related to how far the average delete 1 estimate is from the actual estimate. And then this n-1 is just a factor that was sort of a good estimate of what is the appropriate multiplier to have to get the bias to be an estimate of the true bias. And then the Jackknife estimate of the standard error is n-1 over n times the sum of the squared deviations of the leave one out estimates around the average of the leave one out estimate. So it's sort of like the square root of n-1 times the variance of the leave one out estimates. So again, the rationale for this factor out front, the extra n-1, why not just take the variance of the leave one out estimates as an estimate of the standard error of the statistic? Well, it turns out that the leave one out estimates, because they have the majority of the data, they have n-1 of the data points included, they tend to be quite close to one another, and excessively close to one another. So the variance by itself is not a good estimate of the standard error of the statistic. So we need a factor, and they calibrated that n-1 is a reasonable factor to do that. And the same thing is true with the bias, that the leave one out statistics tend to be a little too close to one another. Unless you sort of multiply this bias estimate by a little bit, you don't get a reasonable estimate. So let's go through an example. So we had 630 measurements of gray matter volume from workers from a lead manufacturing plant. The gray matter volume wound up to be about 589 cubic centimeters, and we want to estimate the bias and the standard error of the median. And then I'll come back to this discussion of jackknifing the median, because that's where we're going to move forward to the Bootstrap. So, for example, the gist of the code to do this, now you don't actually have to execute the code. I'll show you in a page how to do it, but you could do it in any language, not just R. You just have to figure out how to delete observations one at a time. So let's let n just be the number of observations we have. Theta hat is the median of these gray matter volumes. And then the jackknife estimates are the median that I obtain each time where I delete the ith observation, and this sapply function is exactly that. Then theta bar, just exactly from the notation from the previous couple of slides, is just the mean of these leave one out jackknife estimates. Then my bias estimate is going to be n-1 times the difference between theta bar and theta hat. And the standard error is going to be the square root of n-1 times the average squared deviation of the jackknife estimates around the average of the jackknife estimates. And then on the next page, it's a lot easier to do this if you want to just use the software. In the Bootstrap library, you can jackknife out is the jackknife function of my list of gray matter volumes, and the function I want to calculate the jackknife estimate of is the median. And then I assign that to a variable out. Then I pick out the standard error and the bias calculation. Both methods yield an estimated bias of 0 and a standard error of 9.94. And there's an odd little fact. The jackknife tends to work well for sort of smooth functions, and empirical quantiles often don't satisfy that requirement. The median is an example. So there's an odd little fact. The jackknife estimate of the bias for the median is always 0 when the number of observations is even. So the median's an example where the jackknife isn't that good of a thing to do. In general, if your function of the data is a nice smooth function, the estimate that you're getting is a nice smooth function of the data, then the jackknife will work fine. But if not, then it tends to work pretty poorly. And that there was a very well-known paper by Efron, the inventor of the Bootstrap, that illustrated this quite starkly. And the Jackknife has been shown to be a linear approximation of the Bootstrap. So if you're in some setting where it's going to be difficult to program up the Bootstrap, then doing a Jackknife, which is a pretty simple thing to do, is a handy little tool to use. And then just to remind you, don't use the Jackknife for sample quantiles. It's a handy procedure and it works in a lot of settings, but maybe not for sample quantiles like the median, as it's been shown to have some poor properties. And what could you possibly use then? Well, why not try to use the Bootstrap? So let's move on to the Bootstrap, which is maybe a little bit more of a complete toolbox, but is certainly a little less compact of a tool than the Jackknife in exactly the way the analogy to the tools sounds like. By the way, the term bootstrap comes from this idea of pulling one up by one's own bootstraps, right? Of course, this has been discussed a lot. It's kind of an unfortunate title for a statistical procedure because it makes it sound like the information is coming from nowhere, right? Because you can't pull yourself up from your own bootstraps. It's physically impossible. But, there's been plenty of theoretical work that shows where the information is coming from the bootstrap and sort of when it is applicable. Another thing I would note is this idea of pulling oneself up from one's own bootstrap is from the fable of Baron Munchausen. And so there's a great movie called The Adventures of Baron Munchausen, and it was done by some of the people who made the Monty Python series. If you get a chance, you should, in honor of this lecture, watch the Baron Munchausen movie. But anyway, from that fable is where the term pulling oneself up from one's own bootstrap comes from, and then that's where they got the idea for the name for this procedure. Any rate, back to the Jackknife. So another way to think about the Jackknife is this idea of so-called pseudo-observations. So if you take n times theta hat minus n minus 1 times theta hat sub I, you can kind of think of these as whatever observation I contributes to the estimate of theta. And then notice if theta hat is the sample mean, then these pseudo-observations are exactly the data themselves. So it's sort of this idea of taking what worked in a very neat and tidy sense for the sample mean and trying to extend the idea to other statistics. And then the sample standard error of these observations is the Jackknife standard error. And the mean of these observations is a sort of bias-corrected estimate of the parameter that you're interested in. So it takes your ordinary estimate and attempts to correct the bias. I have to admit, for my thinking about the Jackknife, I kind of prefer to think about it this way in terms of the pseudo-observations than in the sort of classical development of it. So now let's get to the Bootstrap. So the Bootstrap is this tremendously useful tool. It's useful for creating confidence intervals, standard errors, basically anything that's involved in the distribution of a statistic where you don't know that distribution. The Bootstrap is an incredibly useful thing to use. As an example, we said before on the previous page that, well, the kind of Jackknife standard error calculation for the median doesn't appear to be working that well, or the bias didn't seem to be working that well, and maybe that raises some question about the standard error calculation for the median using the Jackknife. Well, how about deriving a confidence interval for the median? Or you come up with a generic statistic. You want to look at the log difference of two variances. How do you come up with a confidence interval for the log difference in two variances? Well, the Bootstrap procedure follows from this so-called Bootstrap principle, and you can do things like create confidence intervals for parameters based on kind of difficult to work with statistics. And the Bootstrap principle basically follows along the following lines. Suppose that I have a statistic that estimates some population parameter, but I don't know that it's sampling distribution. So take the median. We actually know a lot about the sampling distribution of the median, but let's suppose you don't know anything about it. Then you would say, well, I'm stuck. Well, the Bootstrap principle says, well, why don't we just take the distribution defined by the data to approximate the sampling distribution of the median? So what's the distribution defined by the data? The distribution defined by the data, if you're not putting any constraints on it, puts probability 1 over n on every data point. That is a distribution. It's a discrete distribution, right? It's a discrete distribution that it puts probability 1 over n on each data point, and it's a weird distribution because the data points, are of course generally have fractional amounts, and it's a weird kind of discrete distribution in that it's not sort of like a die roll where it's on the integers, but nonetheless, it's a nice discrete distribution, and it's mean is, of course, the sample mean. So it's, it's kind of, at any rate, this empirical distribution is a reasonable distribution to work with. And so why don't we look at the sampling distribution of the median based on the empirical distribution from our data, where we place probability 1 over n on each data point. And that's the Bootstrap principle. It's saying, well, I don't know what the population distribution is. And so without that and without some tool like the central limit theorem, I can't figure out what the distribution of my test statistic is. Well, why don't I take my distribution given by my empirical distribution and figure out what the distribution of sample medians are like from that distribution? Because I know that, right? It's just a distribution that's 1 over n on each data point, and I can work with that. So that's a really nifty principle, and it can be executed in a kind of parametric way or a non-parametric way. Today we'll be talking about the non-parametric bootstrap, where the empirical distribution that we work with is just places 1 over n on each data point. If we want to figure out things about this distribution, it's actually not very convenient to work with. Say you have 100 observations, and you're saying, well, the distribution I'm working with now places probability 1 over 100 on every data point, and I want to know what the distribution of medians of 100 observations from that distribution is. That's actually kind of a hard thing to work with. You couldn't actually work that on pen and paper. Maybe if you had, 5 observations, then there's only 32 combinations to work with. But in general, it's a little hard to work with. People said, well, why don't we just use simulation? Forget about it. Why don't we just use simulation? And then the process of bootstrapping has this kind of interesting resampling interpretation. So what do people wind up doing? The general procedure follows by taking the data set and simulating complete data sets with replacement. So we put all of our data points in a bag. Let's say we have 100 data points, and we pull out a new data set of 100 data points, but we sample with replacement. So once we pull out a point and record it, then we put that observation back in the bag, mix it up again, and pull out another point, and it could possibly be that same point again. If we sampled without replacement, we would just get a permutation of our original data set. So the bootstrap distribution is sampling with replacement. So what is that? That is exactly drawing IID samples from a distribution that places probability 1 over n on each data point. And so for every one of these resamples, right, that's the idea. It's resampling from the observed data. You're creating fictitious data sets by resampling from the observed data. That's why it's called a resampling procedure. So let's say we have 100 observations. We draw with replacement complete data sets of size 100 from our observed data. From each of those complete data sets of size 100, we calculate the statistic that we're interested in. Say, for example, the median. We would calculate the median then for every resample. So we draw a sample of size 100, calculate the median. Redraw a sample of size 100, calculate the median. Redraw a sample of size 100, calculate the median. We repeat that process over and over and over again. Let's say we did that 10,000 times. We would get 10,000 resampled sample medians. And we would use those 10,000 resampled sample medians to talk about the empirical distribution of the sample median. And that seems to make a lot of sense. The first time you encounter this, you might think this is the strangest thing I have ever heard in terms of a statistical procedure, but it does make a lot of sense. So let me drone on about this for another couple minutes. So think about if you actually knew the distribution and could sample from it, how you would get to know the distribution of, say, something like the median if you couldn't do the math, which, for most statistics, you can't do the math. Even mathematicians can't do the math. So let's say, for example, I create a distribution. Let's say I have a 100-sided die, and that 100-sided die has probability 1 over 100 for each side of the die. And let's make it at least a little bit interesting. So the die is shaped a little bit funny, so it's not exactly probability 1 over 100 for every number. So you have a distribution on the numbers between 1 and 100. And you wanted to know, what's the sampling distribution of the median of 10 die rolls from this 100-sided die? Well, that's a hard problem. It's difficult to think about how you would work that out on pen and paper. But what you could do is roll the die 10 times, get a sample median, record it, then roll the die 10 times again, get a sample median, and record it. And then roll the die 10 times again, get a sample median, record it. And you could do that thousands of times if you had patience. Let's say, you were waiting for something. And then if you did it enough, you would get exactly the distribution of the sample median. Okay? So you would get exactly the distribution of the sample median of 10 die rolls. And if you wanted to know what the sample distribution of the median of 20 die rolls, well, you'd have to roll the die 20 times, get a sample median, repeat that process over and over again, and that would do it for you. Okay, so now we know if we can actually sample from the population distribution over and over and over again, how we would get the sampling distribution of a statistic. But when we're confronted with real data, we can't roll the die, right? We don't know what the population distribution is, so we can't do it. But what we can do is roll from a die where every side of the die we've put on the number associated with an observed data point. Then we're not drawing from the population distribution, we're drawing from the empirical distribution. Okay? And if we had 10 data points and we want to know what the distribution of the sample median of 10 observations is, well, we can't draw from the population distribution, but what we can do is draw samples of size 10 from the distribution defined by the data we observed and look at what the distribution of the sample median is for those. And that is exactly what the Bootstrap does, is it basically says, well, the Bootstrap in practice via resampling, it basically says, well, we know exactly what we would do if we actually knew what the population distribution was. Why don't we just do that and use the sample distribution and see how that works? And it's sort of a really nifty idea. So again, let's just take our 630 measurements of gray matter volume from workers at a lead manufacturing plant. Then the median gray matter volume is about 589 cubic centimeters. And we want a confidence interval for the median of these measurements. How do we do that? So here's our Bootstrap procedure for calculating confidence interval for the median of a data set of n observations where we know nothing about the sampling distribution of medians of 10 observations. So we would sample n observations with replacement from the observed data, resulting in one simulated complete data set. We would take the median of this simulated complete data set. That would give us one Bootstrap resample and one Bootstrap resampled sample median. Then we would repeat this step b times, let's say, resulting in b simulated medians of n observations, those n observations having been drawn with replacement from the collection of observed data. Then these medians, well, let's say they're approximately draws from the sampling distribution of the median of n observations. And they're exactly draws from the sampling distribution of the median of n observations from the distribution of the observed data, but we're going to say that's approximately equal to the sampling distribution of the median of n observations drawn from the population distribution. That's the leap of faith we're making, is that this Bootstrap process approximates if we, instead of drawing from the observed data, we're drawing from the actual population distribution. Then we could take these b sample medians and draw a histogram of them. And then say we wanted to know, a confidence interval. Why not take the 2.95% confidence interval? Why not take the 2.5th and 97.5th percentiles and call that a confidence interval for the median? And that's exactly a so-called Bootstrap percentile confidence interval. So it's hard to describe, and I know I'm butchering it. And if I were Efron, I'd be doing a much better job at doing this. But unfortunately, you have me and not Efron. And it's difficult to describe, for me at least. On the next page, I'm showing you the R code for doing this, and even I've neatened up the R code a little bit, so it's probably a little bit longer than it needs to be. You could do this in about 4 lines. So here, B is my number of Bootstrap resamples. I said, let's just do it 1,000 times, but you want to set this number B to be big enough so you don't have to worry about the error in your Monte Carlo resampling. You don't want the number of times that you've rolled the die to be a factor in what you're doing. You want to do it a ton. So here I did 1,000, but, crank it up until you're tired of waiting at least. There is a science to how you pick B, but we're not going to talk about it in the class. So N is the length of the number of observations that I have. Okay, then our resamples is this code right here just draws with replacement from the collection of N observations. It draws B complete data sets of size N from that distribution. The replace equals true means that we're sampling with replacement. And then here, this resamples, I dump them all into a matrix so that every row is a complete data set. So there's B rows and N columns. And then I go for every row and I calculate the median in this next line. And that's then B medians, where each median was obtained from resample of N observations from the observed data. And then if you take the standard deviation of these medians, then that is a bootstrap estimate of the standard deviation of the distribution of the sampling mean. If you take the quantiles, the 2.5th and 97.5th quantile, you get 582 to 595. That is a bootstrap confidence interval for the median of gray matter volumes conducted in a non-parametric way. And it's always informative in the Bootstrap to plot a histogram of your resampled, in this case, medians. Okay, so in here is my histogram of my resampled medians, and then the 2.5th and 97.5th quantiles of my Bootstrap resampled medians are drawn here in dashed lines, and so that 95% of my resampled medians lie between these two lines, and so we're going to call that a Bootstrap confidence interval. Now, I'm going to give you some notes on the Bootstrap. So for both the Bootstrap and the Jackknife, today's lecture is really just a teaser. As you can probably guess from my description, they're sufficiently difficult techniques to where, you don't want to take these lectures and view them as enough knowledge to just run out and use them willy-nilly. I just wanted to give you a teaser so that if you hear the terms, you know what people are talking about. So the Bootstrap, the one that I described today, is non-parametric. It makes very little assumptions about the population distribution. And the kind of theoretical arguments proving the validity of the Bootstrap tend to rely on large samples. So there's a question about when and how you can apply it, but I find it to be a very handy tool in general. The confidence interval measure that I gave you, these percentile confidence intervals, they're not very good. You can improve on Bootstrap confidence intervals by correcting the endpoints of the intervals. And the Bootstrap procedure, the one I would recommend is the so-called BCA confidence interval. The Bootstrap package in R will calculate these for you directly if you'd like. That's what these better, when I say here, better percentile Bootstrap confidence intervals correct for bias. And then there's lots and lots of variations in the Bootstrap procedures. There's parametric bootstrapping. There's bootstrapping for time series. You have to do something different for bootstrapping for time series. There's all sorts of different ways to think about the Bootstrap and data resampling in general. And the book called An Introduction to the Bootstrap by Efron and Tibshirani, for anyone who's taken this class, absorbed the material in it, it is at a level that you should be able to understand. It's beautifully written. It's a wonderful treatment of the subject. And then in addition to this, there's lots and lots of other books on the topic of the Bootstrap, probably too many good ones to name, some of them unbelievably theoretical and other ones quite accessible. I think this Efron and Tibshirani book makes a very nice balance between, giving you the why things work and the how to do things combination. And it also covers the Jackknife and other data resampling procedures. The last thing I wanted to mention is I gave you the exact code that you could use to generate for yourself the Bootstrap sampling distribution. You could, of course, use the Bootstrap package in R, which takes about as many lines of code in this case as programming it up yourself. And just on this last slide, I go through actually using the Bootstrap package. But the nice thing about the Bootstrap package is that it will actually give you this bias-corrected interval. In this case, you can see that the bias-corrected interval is nearly identical to the percentile interval, so it didn't make a big difference. But you can, of course, come up with instances where the bias-corrected interval is a little bit better. So that's the end of today's lecture. That was a teaser on the idea of Bootstrap resampling and a little bit on the use of the Jackknife. I hope this inspired you to go learn a little bit more about these tools. They are among the kind of a wide class of tools that became available as modern computing came about, and the idea of being able to use our data, and especially when we have large data sets, to use the data more fully and to use the data to come up with things like sampling distributions instead of using mathematics and assumptions and that sort of thing. So it was a neat idea brought about by the computational revolution, and it's a very nifty technique. Well, next time will be our last lecture, and I look forward to talking about it with you.